Hello and welcome to today's webinar, End of Life Challenge for Flexible Packaging, Multiple Layers and Pouches, brought to you by the BPF and Plastics Consultancy Network. For today's webinar, your host is Dr. Terence Cooper, who has lots of experience within the field and is the founder of Argo Group International and member of the BCN. This Lunch and Learn webinar focuses on challenges faced during the final stage of a packaging's life cycle. Before I hand over to the lovely Terry, just a quick reminder that you can pose your questions to us by submitting them into the questions box on the GoToWebinar control panel. So with that, I'll pass over to Terry.
Thank you for the introduction, Miami, and I'd also like to thank the British Plastics Federation for giving me the opportunity to give this presentation. I am a polymer science and technology consultant, as Miami said, specializing in areas such as bioplastics and recycling and recovery technology, and particularly sustainable packaging. So the end of life challenge for flexible and plastic packaging and for multi-layers and pouches. What I'm going to do is give you an overview of this topic, the advantages of flexible and pouch packaging over other formats, the difficulties of end-of-life mechanical recycling or reuse of flexible packaging, why this is important, the environmental opposition and the industry actions and responses to this, the development of new and improved packaging materials, structures, and recycling and recovery technologies, and then some future developments. So, as I'm sure everybody's noticed, over the last 15 years or so, there's been a transition from rigid to flexible packaging. And why is this? The use of flexible packaging has been increasing rapidly. It's been gaining market share from other formats, particularly rigid. So it's projected to reach, by Smithers, 269 billion in 2024. There's been continual encroachment on areas which have been traditionally used by other types of packaging, particularly in food and beverage and pharmaceuticals. And this growth is coming from the low cost and the versatility of flexible packaging, the continual development of new and improved designs and materials, and the growing focus on consumer convenience. So what is flexible packaging? What's the structure of it? Well, it can be a monolayer, it can be a coated monolayer, it can be a multi-layer structure. And when we have multi-layers, you can see a kind of stylized generic version there. The layers are different materials and they all have specific functions. So they can be bulk layers or appearance layers or barrier layers, printability layers, puncture resistance, tie layers, seal layers, and so on. And these chemically different layers and the fact that it is a film structure cause the difficulty in mechanical recycling. So the diagram there, you have a polyolefin seal layer on the inside, a metal barrier film, a polyamide puncture resistant layer, and a polyester printability and appearance layer. So what are the advantages of flexible packaging? It's superbly designed for first life. There's low content spoilage, long shelf life, low cost, convenience. It's replacing other formats because of its resource efficiency. It provides equal or better functionality than other formats, but uses far less materials, generates less waste, and has lower energy and transport costs. The environmental impact, the life cycle assessment is better, and the carbon footprint emissions are lower than other formats. So the environmental impact to the packaging much less than that of food waste. It can be tailored to specific products and sizes and printed and decorated and coded. It can have high and tunable barrier protection to oxygen and carbon dioxide and moisture vapor. And the consumer convenience fits today's lifestyle. Easy opening, resealability, portion control, zips, dispensers, and so on. So what's not to like? Well, what's not to like is the challenge at end of life because of problems of disposal and recycling, reuse and littering and ocean pollution. First of all, there's worldwide essentially a lack of collection, sorting and recycling infrastructure, particularly for multi-layer laminates, barrier packaging and post-consumer. It's difficult to economically, mechanically recycle films and multi-layers in present MRF equipment, so they're generally landfilled. The low bulk density, so there's less economic incentive to recycle. Printing, because the package is so light, the printing and frequently food residue or contamination can amount to 10% of its weight. And there's high litter visibility. So these are significant problems because of consumer and NGO and governmental, environmental and sustainability concerns, opposition, and potential regulatory action. So the environmental operation, there's been adversarial campaigns from a whole group of NGOs, particularly against food companies using pouch packaging, such as the Kraft Capri Sun. Pressures being placed on food companies to set up takeout programs or stop using pouches. The NGO position is that it's not acceptable to produce a product that's designed to be disposed of. This is based on equating sustainability with mechanical recycling, and it discounts the very substantial sustainability advantages of flexible packaging with regard to the life cycle assessment and greenhouse gases, carbon footprint, and so on, because of its minimal materials, transport, and energy use, and a reduction in product loss. So what's the industry doing about this? Industry is very serious about these challenges. It's actively seeking effective end-of-life solutions to keep flexible packaging from landfill or from litter and ocean pollution and make sure it takes part in the circular economy. Companies and brands are setting sustainability and recycled content goals with the Ellen MacArthur Foundation and plastic pack commitments and probably coming extended producer responsibility legislation to mandate collection. And the industry realizes it has to further increase the packaging resource efficiency. And a lot of different approaches are under development that we'll now talk about. So major initiatives and technology developments. The first two of these are for mechanical recycling, enhanced collection, identification, marking and sorting systems, and mechanical recycling technologies. And I'll talk about 3 projects here. And secondly, improved materials and designs for recyclability and development of mechanically recycled monomaterial structures to replace pleasant multi-layer structures while still providing high barrier properties and puncture resistance and printability, sealability, stiffness, and optical properties. And we'll move on to physical and solution type recycling, delamination, selective extraction processes, chemical, and then the last 2 are chemical recycling types with depolymerization to take them back to their monomers, which can then be repolymerized into new virgin material, or starved oxygen, where this isn't practical, starved oxygen and anaerobic gasification and hydrothermic liquefaction to produce new naphtha feedstocks and oils and syngas and so on, which can then be used to make more new polymers and chemicals. So moving into mechanical recycling, the first project I'd like to mention is Materials Recovery for the Future. This is in the US. It's a consortium of brand owners. You can see, led by the American Chemical Council, you can see a whole range of companies that are involved. The goal here is to increase the recycling rates, divert flexible packaging from landfill, and create mainstream recovery processes and systems. So the American Chemistry Council has been working with a consultancy called Resource Recycling Systems and their research, and also with JP Mascara, which is has a MRF in Pennsylvania. And their research has shown that modifications of existing screening and also using upgraded optical sorting technology can efficiently identify and sort flexible packaging from single stream residential curbside collections with a 74% recapture rate. That they want to get up to 90%. And this provides a new recovered flexible plastic material stream and also improves the quality of other streams, particularly the paper stream. So this has shown the technical and economic feasibility for recycling waste flexible plastics, and also identified some potential end-use markets. So the question now is whether MRFs will be willing to put in the kind of investment required for this, and so that the flexible packaging can be added to residential curbside collections, single stream collections in the US. Secondly, the CFlex project in Europe, that's circular economy for flexible packaging. It's a very, very ambitious project. It now has about 154 companies, last time I looked, supporting it. And it represents the entire European flexible packaging value chain. They started off by developing, it's been going for about 4 years, developing design for circular economy guidelines. This involves not just guidelines for flexible packaging designs, but also for the end-of-life collection and sorting and recycling and recovery and the infrastructure for this. And this is now being implemented. And the goals by 2025 are to make flexible packaging sustainable and valuable in the circular economy, to have end-of-life value, stop it becoming waste or marine litter, to demonstrate sustainable, robust business case for circular economy for flexible packaging, to maximize the overall resource efficiency and optimize recyclability, and then to establish collection, sorting, and reprocessing infrastructure for flexible packaging across Europe. And finally, to ensure that the flexible packaging is actually recycled, not just recyclable, and that the recyclers find sustainable end markets to replace virgin materials. I can't put up 150 stakeholders, but you can see here some of the big companies involved initially, everything from polymer producers, packaging converters, brand owners, retailers, sorters, recyclers, collectors, machinery suppliers, end users, and everyone else. Third project I'd like to talk about is the Holy Grail Digital Watermark project in the EU. This is aimed at providing improved identification and sorting, because ineffective, you can have collection, but if ineffective identification and sorting is then a very big obstacle to lightweight packaging, waste recycling, and achieving circular economy. And improved identification and sorting also gives more efficient mechanical recycling and higher quality recyclates. This began in 2016 as a pilot project, about 30 companies led by Procter & Gamble and the Ellen MacArthur Foundation, was very successful following it, and now expanded to 120 plus companies led by the European Brands Association. And the goal is to prove the viability of digital watermarking technologies to efficiently enable the polymer identification of packaging, sorting, and high quality recycling at high throughput, to launch an industrial pilot for this and demonstrate a large scale business case. And just to show the digital watermarks are small machine readable codes. They're about the size of a QR code, but invisible to the eye. and they're incorporated on the packaging surface in multiple positions and record and provide detailed information about the polymer types, the multi-layer structure and composition, whether it's food or non-food, the manufacturer, the converter, the stock keeping unit, and also allows for inventory control. The next area I'd like to describe is the development of single polymer monomaterial barrier and pouches to replace multi-layers, which are hard to recycle. So these are mechanically recycled monomaterials, which are processable on conventional equipment and comply with the Sustainable Packaging Coalition's How to Recycle Store Drop-Off programs in the US. They're cost-effective all polyethylene or all polypropylene replacements for multi-layer laminates, which are not mechanically recyclable. And they have enhanced optical properties and gloss and tensile and tear strength. This was started off essentially by two companies, Nova Chemicals with their I-beam structures. And there's an example of the kind of structure that Nova Chemicals came out with enhanced barrier properties, acceptable for food packaging, good opticals, high stiffness, puncture resistance, sealability. The other company is Dow Chemical with its recycle ready technology using HDPE and single site linear low density polyethylene. Again, very good physical properties, good barrier properties, and if very high oxygen barrier is required, an EVOH layer can be incorporated, and it's considered that the incorporation of less than 5% by weight barrier or coatings is still considered a monomaterial. So this is to give you an idea of what Dow developed, replacing the recyclable structure on the left there, which is multi-material with PET and PE and also a barrier layer of some kind. Replacing that with a recycle-ready structure, a monomaterial structure on the right, which is mostly polyethylene of different types with different types of polyethylenes for different functions like heat resistance and the sealing layer on the bottom there. These can incorporate an oxygen barrier such as EVOH. And if that's done to make them, again, recyclable, a compatibilizer is incorporated as part of one of the HDPE layers. Now, here's some examples of these from Dow. And compatibilizers have been developed to aid the recycling of the oxygen barrier flexible packaging. What's a compatibilizer? These are molecules which contain different functional groups so that they grab on to different incompatible polymers and help them mix together. So by doing this, you can increase the actual recyclability of the flexible barrier packaging and minimize the environmental impact and reduce the material landfill. Good examples of these compatibilizers are Dow Chemicals Retain and Amperset Revised materials. These allow the barrier packaging and pouches that cannot normally be mechanically recycled to be mechanically recycled in a polyethylene recycling stream. And the systems containing ethylene vinyl alcohol and a compatibilizer have qualified under the How to Recycle Store Drop-Off program. The compatibilizer is incorporated in a high-density polyethylene layer, and when the material is recycled and the polymers are melted, it disperses the ethylene vinyl alcohol, or if there's a polyamide layer in there, in very small domains, smaller than the wavelength of visible light, so that the polyethylene is still transparent and it can be reused. although of course the ethylene vinyl alcohol or PA layers are no longer present as layers. And Dow's collaborated with Kellogg on this for dry food packaging. Here's an example of a Kellogg's granola, fully recyclable, all PE stand-up barrier pouch. So a 9-layer structure, incorporating EVOH and retain compatibilizer with high oxygen and moisture barrier, and approved for how to recycle. These monomaterials technology is now being developed considerably further, and the pouch structures are rapidly advancing in design types and applications for a whole range of products. PE is the most widely used material so far. Polypropylene is growing rapidly. The barrier properties of both of these are improved by orientation. And these new advanced monomaterial structures provide high water vapor barrier, high puncture resistance, printability, stiffness, down gaugeability, and lightweighting and optical properties. So they can replace structures containing PE multi-layers or PEPA. And there are now also retortable packages which require all polypropylene designs. The all polyethylene pouches can be made by co-extrusion or lamination. They contain multiple layers, between 3 and 12 layers, depending on the application and the property requirements. It's important, though, to recognize that the processing is a little more tricky than using traditional multi-material laminates, and you need processing equipment which allows for accurate thin layer and layer ratio control. And the monomaterial pouches generally have to be optimized for specific applications and the nature of the packaged goods and the line conditions. So these advanced structures incorporate specialty high-performance PE polymers, such as metallocene LLDPE and polyolefin plastomers. Oriented films can be low density, biaxially oriented polyethylene or polypropylene, cast polypropylene, and also nucleated high density polyethylene. These films are more expensive than conventional films, but they give all of the enhanced properties I've just mentioned. For example, the machine direction oriented PE structures have exceptional stiffness and clarity. And a lot of companies are now moving into this field, including, of course, Dow and Nova that started it off, quickly followed by ExxonMobil and SABIC, and then others. Many produce processes and converters, such as Amcor with Nestle, which has developed the first recyclable barrier retortable pouches. Bob's with Dow, for example, a lot of different development there, and Mondi with Jindal and Unilever. And of course, the orientation and material suppliers. Also coming along, the development of barrier coatings and adhesives to replace the polymer layers. These are extremely thin, a few nanometers. Barrier coatings, adhesives, tie layers, which don't compromise mechanical recyclability, but provide high oxygen barrier and allow lightweighting and reduction in the number of layers. So good examples of these, SiOX, ALOX, coatings, nanoclays and acrylate coatings, nanofibrillated nanocrystalline cellulosics, and then a different group of materials which still allow recycling because during the washing process in the recycling, they either hydrolyze or dissolve and disappear in the sewer system, where they are biodegraded. So these would be things like polyvinyl alcohol, polyglycolic acid, whey proteins, and hydroxypropylated starch. It's important to recognize, though, that all of these monomaterial structures we mentioned, they all require collection and sorting. So either you have to collect them curbside and put into curbside collection, or by store drop-off. And whether the consumer is going to do this is a key factor. And you can have problems of film contamination, particularly food waste. So you really need clean film. Here's an example of lightweighting where we're going from a kind of generic commercial 3-ply laminate there with a metallic or metal layer barrier in the middle to a barrier coating, which allows us to take this down to a 2-ply laminate, make it much simpler. Moving on from mechanical recycling now, what I call physical recycling, although some people will call this chemical recycling. These are things like delamination, selective extraction and dissolution processes, which can also provide de-inking. Here, the original polymer structure and its energy content are retained, essentially just like mechanical recycling with enhanced purification steps. So we still have the challenge of collection and identification and sorting to get enough volumes to make it economic. And these processes are complementary, not competitive with mechanical recycling, and they're aimed at handling waste that cannot be processed by mechanical recycling, such as multi-layers and heavy contamination, and to increase the quality of the recyclates. First one I want to mention is the Superatec delamination process in Germany. This is a low energy physical and mechanical recycling process for multi-layers. Here the packaging is shredded and surfactant-based microemulsions are used to break up and separate the layers. The microemulsions reused, works with formats incorporating plastic layers and paper and aluminum, and you get back high purity plastic components and aluminum and cellulosic fibers, which can be reused. It's originally developed for rigid packaging, but extended to flexible packaging. There's been a pilot plant in Germany since 2014. They're looking to build a large-scale center, and Henkel made a big investment in this company back in 2019. Secondly, Cadel de-inking in Spain. This is technology to de-ink, originally surface printed packaging using a solvent-free alkaline surfactant solution. Cadel's looking for licensees of the patented technology. Removes ink from polypropylene PE or PET, gives a light-colored recyclate or clear recyclate, and their development now is focusing on post-consumer packaging. They have a pilot plant in Spain. It works with water-based and solvent-based UV and electron beam inks. And the de-inking surfactant and rinse water can be recovered and recycled. And Cadel is working to improve the economics to ensure that the financial benefit of producing the clear or light colored recyclate compensates for the additional cost of the ink removal. Cadel has also adapted this process now in the lab to separate multi-layer structures for recycling and to de-ink non-surface printing applied between these layers. Some selective extraction processes, APK new cycling and Fraunhofer creosol dissolution processes, both in Germany. These are for multi-layer and mixed plastics to give properties with close to virgin materials, and they claim competitive economics. The polymers here, this is a little different from the last two processes. The polymers are selectively dissolved from the plastic waste with customized solvents. This removes contaminants, and the pure polymers are recovered from solution and pelletized, and the solvents are recycled. So APK already has commercial products here for LDPE and also polyamide. Secondly, the pure cycle process for polypropylene, originally a spin-off from Procter & Gamble. This uses high pressure supercritical extraction and filtration with alkaline solvents, where the polypropylene is insoluble now, but the impurities are soluble, and produces recycled polypropylene with virgin properties that they hope to be make suitable for food contact, and they're constructing a 50,000 ton per annum polypropylene plant in Ohio to be operational later this year. And according to PureCycle, their output for the next 20 years is already pre-sold. Let's move on now to chemical or advanced molecular recycling and recovery. All of these terms have been used. These are emerging technologies that require more energy. They're currently more expensive than mechanical recycling. So this would include depolymerization processes where the original polymers are broken down into monomers, which can be repolymerized. And it's currently applicable to polyesters and to polystyrene. And on a pilot basis, BAS is developing for polyamides with that chem cycle process. Secondly, second category would be thermal oxidative processes to make functional chemicals. That's a very infant area. And thirdly, gasification, pyrolysis, plasma pyrolysis, hydrothermal liquefaction processes where it's impractical or uneconomic to go back to monomers. And here the polymers are converted to syngas for carbon monoxide and hydrogen, or to feedstocks such as naphtha and pyrolysis oils, which can be used to make new polymers. Again, these chemical recycling processes are complementary, not competitive to mechanical recycle, and they're aimed to handle waste that cannot be processed by mechanical recycling. So to start with, we'll talk about some depolymerization processes for polyesters. The advanced circular recycling technologies for polyester waste, especially for food packaging and low quality feedstocks, which are not mechanically recycling. These processes work for colored and filled and dirty and food contaminated post-consumer waste. They don't generally need unwashing or sorting. They're converted. The polyesters go back into parent monomers, which can then be repolymerized to high quality virgin polyesters, so suitable for food contact. It's generally high energy, high cost, but it produces high value recycled products from what would otherwise be non-recyclable waste. Here's some examples of processes for polyesters. There are many of these under development. I just wanted to show a range of some of the different types. Volatile catalysts, like for the IBM Volcat process, catalytic processes like the Ionica, Unilever, Indorama, Coca-Cola, the Eastman glycolysis and methanolysis processes, where they aim to have a commercial plant in 2022. Loop Industries in Canada, together with Suez and Indorama. This is claimed to be a low energy, low temperature, no pressure process, but right now it's rather controversial, although they're projecting a commercial plant in Europe in 2023. A fast microwave process coming out of Switzerland. And finally, from France, the Carbios enzymatic biorecycling process, where they are looking to have a pilot by the end of this year and to be commercial by 2025. Chemical recycling. The second category would be the Novaloop process. This is very new, developed by a startup company in California. It used to be called Bioselection. So accelerated thermal oxidative decomposition for polyethylene of different types. So use dual catalyst oxidation at fairly low temperature and atmospheric pressure, making low molecular weight functionalized organic compounds like alcohols, aldehydes, ketones, and diacids. The oxidation systems are very active. They remove things like PE additives and impurities. and produce especially a range of dicarboxylic acids, C2 to C10 at 90% yield based on the PE, and you can tune this ratio based on the of diacids. Their present emphasis, though, is making high-value products from the diacids, and particularly conversion to polyester polyols and then to thermoplastic polyurethane elastomers, which have up to 45% recycled content. And this is a very good example of upcycling. You have polyethylene waste, which might be worth 75 cents a pound, and they're converting it into thermoplastic polyurethanes, which are probably selling for around $15 a pound. Their current work's aimed at post-consumer PE films from MRFs, and eventually they want to make this work for multi-layer systems. And the third big area for chemical recycling, these are gasification, pyrolysis, and hydrothermal liquefaction processes, starved oxygen processes to produce naphtha feedstocks or pyrolysis oils or hydrocarbon waxes or syngas, and these can then be used to make new polymers, downstream chemicals, or even liquid fuels. And this has a major application for polyolefin waste, which cannot be mechanically recycled or depolymerized to polymers in an effective way. The advantages of these processes is that mixed packaging and plastics can be used, although they generally want to avoid PVC and high levels of oxygenated materials like PET. So this avoids the necessity to very meticulously identify, sort, and separate different types of packaging waste. And there's no solid plastic recyclate, so there's no market to be found for that. The disadvantage is that some NGOs and consumers do not consider this to be true recycling, and the processes that are being developed are still controversial. And it's vital to recognize as part of this that these processes are quite different from incineration, which is an aerobic process and produces CO2. They have very low emissions and greenhouse gas footprint, and they yield useful chemical products, which can be converted back into new materials. So here's some examples. There's a great many of these being developed at the moment. I'm just picking some examples to show you the breadth of the types of technology being developed. Enerchem in Canada with a fluid-based bed gasification produces syngas, and then that's catalytically converted to methanol or ethanol and downstream chemicals. They have a 10,000 ton a year plant in Edmonton in Alberta, and they're planning plants in Canada and Spain and the US and in other parts of Europe and China. British Airways with Velasys have developed a thermal gasification for plastics and other waste to make syngas and then jet fuel and diesel and also naphtha. They're building a 20,000 gallon per annum jet fuel plant in Immingham, UK, and also will make naphtha. Brightmark Energy, waste pyrolysis to low sulfur diesel, naphtha, and waxes, and they are aiming to source enormous volumes of plastic scrap from the eastern US over this year and next year. Plastic Energy with SABIC, anaerobic gasification to make hydrocarbon oils, which can then be used as feedstocks for new polymers and chemicals. They have 2 plants in Spain and many more planned. The Eastman carbon renewal technology, oxidation of syngas, conversion to methanol and acetic acid, which is then used in their other production processes, such as to make cellulosic polymers. And they have a commercial plant in Kingston, Tennessee. Phoenix in Holland with Dow, again, pyrolysis process to make naphtha and paraffins, which Dow is then using to make as a feedstock for their new polymers. Recycling Technologies in Swindon, thermal fluidized bed depolymerization to oils and waxes. They have a pilot facility in Swindon and a commercial plant in Perth, Scotland, and others being built in Europe. Green Mantra in Canada, a similar kind of thermocatalytic depolymerization to make waxes with the plant in Ontario. And finally, Lysella from Australia and working with Mura Technology in Europe, a catalytic hydrothermal liquefaction using supercritical water. And this converts the waste plastics into what they call biocrude oil, which is then used as a feedstock for making new plastics and chemicals. They're constructing a plant in Teesside, which should be operational next year, and others are planned in the US and Germany. So you can see the breadth of the types of processes being developed in all these chemical recycling types. Here's an illustration of the Enerchem process from sorting municipal solid waste and plastics waste, converting to gasification, converting to syngas, cleaning the syngas, and then catalytically converting that to methanol, ethanol, biofuels, chemicals, and so on. So just as another example, the recycling technologies process, just to show you the range of carbon content, carbon distribution that can produce, everything from oils, chemicals and oils up to waxes. And finally, a little bit different, the NVAL process. And here the goal is mainly aluminum recovery. This is a spin-off from Cambridge University, provides environmentally favorable end-of-life process for completely recycling post-consumer barrier pouches and tubes made from plastics and aluminum laminates. They were supported by Nestle and Kraft and Multilayers to construct a commercial plant and scale plant in Alconbury in the UK, using continuous anaerobic microwave-induced pyrolysis over a carbon bed at high temperature to recover 100% of the clean aluminum ready for reuse, and at a much lower carbon footprint than making new aluminum. The plastic components are converted to a fuel gas to power the process and to high alkane liquids similar to diesel fuel, which can also be used as feedstocks. Once again, we still have the challenge of collection, identification, and sorting to get requisite volumes in a given geographic area of the aluminum-based barrier packaging. So to summarize, flexible packaging, particularly multi-layer and pouch packaging, has significant advantages and its use has been expanding. It's resource efficient, ecologically advantageous because of low materials and energy use, low carbon footprint, and greenhouse gas emissions, and reduction in food waste. It's still under attack by environmental groups because of the difficulty of economic mechanical recycling. So that it's often mostly landfill right now, and also because of the environmental group war against ocean pollution and single-use packaging. And the industries are responding strongly to this by developing improved mechanical recycling and collection, identification, and sorting technologies, new materials and structures and designs, and incorporation of recycled content, new recycling and recovery technologies, including delamination, dissolution, depolymerization, conversion of monomers and feedstocks and chemicals and so on, and the implementation of these various potential routes and processes will depend on local and national logistical, economic, social, legislative, regulatory, and political situations, not just technological factors. And that's a very important last point. So thank you. With that, I'd like to thank you for your interest, and I'll try to answer any questions.
Great
Over
stuff.
to you, Miami.
Yes, great stuff. Thanks a lot, Terry. That was a really, really insightful and great presentation. Loads of comments about how brilliant it is and how amazing you are, which is awesome. I agree, of course. So we've got a couple of questions come in, and I just want to kind of like read them out to you. How long will it take before there is a big infrastructure for chemical recycling that could be put in place? That's the first one.
Obviously, there's a lot of development going on with the processes. In fact, there was a report done by a big industry group in the US on chemical recycling technologies, and they came up just in North America with over 50 different types of chemical recycling technology that were being developed. So you can see this is a huge area, and but there also, on the other hand, there's a lot of obstacles. And first of all, high energy use and high cost of these processes right now. So they're not going to be used where you can use mechanical recycling, but they can be used for a lot of contaminated materials which you can't use mechanical recycling for. So Closed Loop Partners in the US did this report. They're very much pushing for these types of processes, but there's a lot of controversy about this and opposition from environmental groups, many of which seem to not realize the difference between chemical recycling processes and incineration processes for energy. So I would say it's going to be, before we have a big infrastructure of viable processes, it's going to be at least another 10 years. And obviously some companies have processes out there working now. One I didn't mention, Nexus in the US, has a process which is making feedstocks which are being used by Shell in its refineries, for example. So these things are coming, but it is going to take a little while before it becomes what you might call the norm.
That's great. That's fine. Yeah. And then we've got another question here. What are your thoughts on the Demoto microwave process? I'm not sure I've said that right. Do you think it's a lead idea?
Demoto. Which one was that? Are you talking about the Swiss program, the GR3N?
Potentially. I didn't write the question.
Well, that one seems to be. I mean, that's in a very much in the developmental stage, but it seems to be highly efficient. These microwave processes seem to be highly efficient. The MVAL process, they're trying to bring this out into the industry now and get put together a consortium, basically, of companies that want to use this type of process to recover aluminum and also the plastic components at the same time. And I think we're going to see some movement on that. That's a well-developed process now, at least technically.
Yes, and I have got clarification that yes, it was in reference to the Swiss idea. So that's good.
Okay. Yeah.
Awesome. And then we've got another question. Recycled polyolefins now cost about, well, it's not really a question actually, it's more of a rhetorical question. Recycled polyolefins now cost about the same as virgin polymers. Maybe now is the time to explore other uses for waste plastics?
I think actually there have been quite a few instances over the last year or so where recycled polymers have actually been selling for more than virgin polymers. That's largely, or not largely, but one reason is that because of, especially in North America, where where polyolefins are made from natural gas, especially cheap frack gas, rather than from oil. The price of polyolefins, the virgin polyolefins, has been quite low. It's been going up very recently, although I suspect it's going down again. And because of that, it's difficult to compete on price with recycle, even with mechanical recycle. So what I think we're going to see is that people, companies, brand companies especially, because of all these commitments they've made to Ellen MacArthur and plastic packs and so on about use of recycled content, they're going to end up just for green marketing purposes and to show their sustainability, they're going to end up paying maybe even more for the recyclate than for virgin polymers. It's a very strange situation, but that seems to be the way it's been going over the last year.
Yeah, strange times are currently happening, so we don't know how much that's gonna maybe impact or not with everything happening with the pandemic and stuff. So why are gasifications considered controversial by NGOs? That's another question.
This is this is a very if you look at some of the reports that come out from Greenpeace and Gaia, which is I can't remember what that stands for now, but they're against any kind of it's a group which is against the use of incineration, but they're also against the use of chemical recycling, even though chemical recycling is nothing like incineration. So their major kinds of arguments are people have been trying to develop these and make them economic for years and years. There have been examples of processes that were scaled up and then didn't work properly because of the lack of control of feedstocks and so on. What they seem to be saying is nobody's made it work yet, which isn't actually true. We've got the examples of people like Plastic Energy, and it's not going to work in the future. Especially, it's going to take a lot of energy, and they don't seem to be willing to allow the industry to do or credit the industry with all this development work that's going on. As I said, over 50 different types of projects going on in North America alone to be able to develop these processes and make them good. The other argument they have is that this is really not a reputable kind of development, in the sense that it's just a way for the plastics companies to make it look as if it's another form of greenwashing, for them to make it look as if they're trying to solve the plastics waste problem and recycle and so on by these development of these types of chemical recycling processes. Whereas really it's just a way for them to do business, the plastics and polymer companies to do business as usual. That's the kind of arguments that they're making, and unfortunately they often resonate with consumers and with governments and so on.
Great. And then we've also got another question in lead up to that, and what makes the loop process controversial as well?
The question, the reason that was controversial is that there was a study put out by a company called Hindenburg, which is a financial company basically, which claims that they've been they had interviewed all kinds of ex-employees and everything like that, and that the loop company had been overstating the ability and the developmental stage of their technology, and that Loop came back and said two things which are quite telling in a way. Number one, that the comments were applicable to their very first technology, but they're now on a second generation, which is what they were talking about with low temperature and low pressure. And secondly, that Hindenburg are actually short sellers, and they've been trying to short sell the Loop stock and make money that way. So they have a vested interest in making them look bad. I ought to add that Hindenburg are now trying to do this with PureCycle. Is it Hindenburg? There's another company, at least with short seller, trying to do this with PureCycle as well. So you have to be very careful how you interpret some of these things. And really, the question, the solution here is to wait and see what happens, and the proof of the pudding will be when it comes to fruition in the eating. Do Loop really set up this plant with Indorama in the US and this with Suez in Europe?
Great. I'm conscious of time, so this is the last question, I'm afraid. Thank you to everyone who's been sending in questions and comments. These will all be relayed to Terry himself. And if you do have questions further on from now, do send them in to us at events@bpf.co.uk. So the last question that I'm about to end with is, this person has written, I am still perplexed how a structure with 5% EVOH can be considered a monolayer. This was stressed in a talk by another company yesterday when they called their strata film all polypropylene. How is this type of product marked with a recycling label?
That's an interesting point. that has been kind of I won't say an industry standard, but that's been like a convention for the last few years, that putting less than 5% of a barrier layer, for example, like EVOH in, it's still considered a monolayer. Where that came from, I really don't know. And I suppose the real what it really means is, if you have that lower layer, a level of say EVOH, and then you recycle mechanically the polyethylene structure, it can still be recycled. It can still act. It still can be processed, but it will have somewhat poorer optical properties. So you have to be careful what you recycle it into. Why that 5% was selected, I don't know, but certainly that's the kind of the monomaterial producers. That's what they quote. 5% is still considered monomaterial.
Thanks for clarifying that one. And sadly, as I said, we are out of time. As ever, a copy of this presentation, along with the video of this presentation, will be sent out to you as soon as possible. Huge thanks again to Terry and to all of the PCN and everyone who has listened in. And have you got any final words, Terry, before I sign off?
Simply that this is a very important topic. We have a packaging format which is incredibly resource efficient, and we vitally need to make sure that we develop efficient end-of-life technologies so that we can continue to take advantage of this resource efficiency and of flexible packaging, and not, excuse me, of flexible packaging. Let me leave it at that.
Very wise words. Thanks a lot again, and we look forward to working with you again soon and the rest of the PCN. There are a few PCN webinars coming up. All details of those can be found on the BPF website. So I'm about to sign off. Thanks a lot and have a great rest of the week.